Okay, all right, so we're good now. Yeah, thanks.
All right, yeah, thank you very much for the introduction. So today I'll be describing some of the work we've been doing over the past 10 years or so in the field of nonlinear model reduction, where really what we're trying to do is employ machine learning to enable rapid simulation of extreme scale physics models. And I think as you'll see in this talk, and as you've seen in previous talks, we're really using machine learning tools for sort of a new type of application. We're not trying to necessarily, predict pictures of cats or classify, images in certain ways. We're trying to actually accelerate extreme scale physics simulations, which requires a totally different approach to AI and how those tools intersect with computational physics. And a lot of the new work I'm presenting today was done primarily by my former postdocs, Kuk-Jin Lee and Eric Parrish, who are at Sandia National Labs. Okay, so the motivation for this work is as follows. So as many of us know, a high fidelity physics-based modeling and simulation has become indispensable across a wide range of applications in science, engineering, and even entertainment, as it provides a mechanism to accurately simulate realistic performance of complex engineered systems or virtual agents. However, to obtain high predictive fidelity, in many cases, we must imbue our models with very fine spatiotemporal resolution, which can lead to extreme scale models whose simulation consumes months on supercomputers. So here are a few graphics from some of my former colleagues at Sandia. Simulations, whether they correspond to turbulent reacting flows, modeling the Antarctic ice sheet, or MHD simulations. It's not uncommon for these simulations to be characterized by hundreds of millions of degrees of freedom and hundreds of thousands of time steps. And as a result, and this is something that research engineers face on a daily basis, there's a de facto computational barrier that prevents us from using truly high predictive models with true high predictive fidelity for a range of time-critical problems where simulations must execute on the order of seconds or minutes. So examples of these applications are model predictive control, health monitoring, devising an interactive virtual environment, as well as design optimization. And some of my recent work in my current employer is taking me into this sort of interactive virtual space where you can imagine any interaction with a virtual object needing to require real-time rendering if we want these interactions to be realistic. So for example, simulating surgical operations, we must have high fidelity models to make that interaction realistic. So really the overarching goal of our research thrust is to break this barrier such that we can use these high fidelity predictive models for a range of important time critical problems that to this point were just simply not addressable with high fidelity models. So one example that I worked on in my previous life is the so-called captive carry problem, which is essentially trying to simulate the long time pressure exerted on a store when it's immersed in a three-dimensional cavity on an aircraft. And really the goal of this analysis is to basically perform that computation over a range of Mach numbers and angles of attack. So Sandia analysts, in particular Matthew Baroni and his coworkers, developed a highly predictive fluid structure interaction model. On the left, I'm visualizing sort of the store and the associated structural deformations, as well as the pressure exerted on that store. And on the right, I'm visualizing a two-dimensional slice through that three-dimensional cavity, and I'm visualizing the gradient of the density. And this model was developed over the course of about a year. And they were quite happy with the predictive fidelity in the sense that it matched wind tunnel experiments to within 5% in the quantity of interest, which is in this case, it was the drag exerted over that store over, a wide range of Mach numbers and angles of attack. But the price that was paid for this is obviously, fine spatiotemporal resolution. So the model on the right, just the CFD model, is characterized by 100 million cells and 200,000 time steps, such that one single simulation consumed 6 weeks on 5,000 cores. So to give you an idea of how costly that is, even at Sandia, where we have, where we had access to very large scale computing resources, just 5 of these runs going concurrently maxed out our allocation on our supercomputer. So that really placed a de facto barrier between this model and envisioned use cases that we would like to use this model for, like doing complete exploration of the flight envelope, performing real uncertainty quantification, so quantifying the sort of effect of uncertainties in the environment, in manufacturing, and sort of aging on the resulting performance of this engineered system, model predictive control, and robust design of the store and cavity. So again, our goal is to break this barrier so we can use these models for these problems. And one final motivation slide. Some of you may have seen a few years ago, NASA issued a high-performance fast computing challenge where they actually articulated this very computational barrier. They mentioned in their challenge that CFD tools are too slow for complex geometry flows. They take thousands to millions of core hours. The example I showed in the last slide actually corresponded to 5 million core hours, so it's right in the wheelhouse of this call. And they want to enable high-fidelity CFD for multidisciplinary analysis and design. which is their time critical problem. And what they're after is sort of an acceleration of existing calculations by between 1 and 3 orders of magnitude. And I'll hope to convince you in this talk that we've already basically hit this articulated criteria for some interesting turbulent flows. So this is sort of the setup why we're doing this work. And as you can see at this point, this is not a sort of common machine learning task that we often read about in the literature, right? We're not really training reinforcement learning agents. We're not doing classification or regression. We're trying to accelerate large-scale simulations. So how can we go about leveraging AI innovations for this purpose? So we'll start off with our general mathematical formulation. So I'm going to start with our high fidelity or full order model, which I'll abbreviate as FOM in this talk, as just a parameterized system of nonlinear ODEs, which I've written here. So we imagine X to be a state vector. Say this is of length 100 million. Often this is the solution variable discretized in space. F is the velocity vector, which we're going to assume is nonlinear in its first argument. We have some parameterized initial condition, some finite time interval, and we allow our parameters mu to live in. That defines an initial value problem or a full trajectory or simulation. So with this view of a parameterized system of nonlinear ODEs, what is a time critical problem? A time critical problem is merely one that states that we would like to rapidly solve this ODE for arbitrary points in parameter space. And of course, the time constraint here depends a lot on the application. It could be a millisecond, it could be a few seconds, or it could be a few hours, depending on what you're after. But the point is that for many different configurations of the system, we want to solve the resulting model rather quickly. And so to get at this, to make progress in this, what we're going to do is exploit sort of the following concept, which is we're going to exploit simulation data collected at a small number of these configurations or points. And this will always be done in sort of 3 sort of general steps. First is training, where we pay the price of solving our expensive model at a handful of these points shown in red. And during the course of those solutions, we're going to collect simulation data, which I will particularize later in the talk. Number 2 is we apply machine learning. So in this talk, I'll present a variety of unsupervised and supervised machine learning methods that we deploy on those training data. And step 3 is that we leverage the structure or models that we build in step 2 to drastically reduce the cost of solving the ODE at the remaining query points. So we're sort of fitting into the traditional training and deployment paradigm of traditional machine learning. But in our case, the data source is actually our high fidelity model itself, which we're going to run a handful of times. So I will first, before getting into some of the recent innovations we've pursued, I will first sort of describe how this has been done historically in the field of model reduction. So step 1, as I promised, is training, where we solve this high fidelity model for different points in parameter space. So we take our ODE system and we pick one point in parameter space and we solve it. And so what we do at each time step here is we save the state vector X and we concatenate these together as columns in a so-called snapshot matrix. The dimensions of the snapshot matrix are n by t. N is the number of degrees of freedom in our model. Again, it's about 100 million. And t is the number of time steps we've taken in our simulation. Say that's on the order of 100,000. So we complete this training study at different points in parameter space to form this sort of global snapshot matrix. And so if you're familiar with POD or traditional model reduction, you know what's done next. The quote machine learning method, which has actually been around for over 100 years in the form of PCA, is we simply apply compute the singular value decomposition of this matrix. And then we truncate the left singular vectors and preserve only the dominant modes. And from a machine learning viewpoint, these are basically the principal components of the spatial simulation data that we've calculated. So I'll explain later on how we improve this with innovations from deep learning, but this is sort of what has been done for decades in our field. So now that we've executed steps 1 and 2, what do typical model reduction methods do? They reduce the cost of solving the ODE system via a projection process. So in particular, we make the assumption that our state lives in the low dimensional subspace spanned by the columns of phi. So we approximate X as X tilde, which is enforced to be a linear combination of these columns of phi. And if we have envisioned this X hat vector to be of length roughly 100, we've reduced the dimensionality, from 100 million down to about 100. So given that kinematic approximation, how do we reduce the dimensionality of our dynamical system? So recall our full order model ODE. I'm going to suppress the dependence on the parameters just for notational simplicity. But at a given parameter instance, this is our high fidelity model ODE, which you can write as basically the time continuous ODE residual is equal to 0, where I've defined this ODE residual to be the misfit of the left and right hand sides of the ODE. So given this description of the high fidelity model, the way that the most popular method in our field has operated is basically via Galerkin projection. So the way this works is we take this phi matrix and we perform Galerkin projection, which yields the top right model, which is just, dx hat dt equals phi transpose f of phi and x hat. And we showed in our paper that this is actually equivalent to a residual minimizing approximation carried out on the ODE residual. So you can convince yourself that this is the same model as what is shown below, which is this optimization statement. And that arises from the fact that phi is an orthogonal matrix. So we have two ODE models, a Galerkin and a high fidelity model, ODE model. Of course, we know to numerically solve those models, we must introduce a time discretization method. If we use a linear multi-step scheme, then we yield a system of nonlinear algebraic equations that must be solved at each time step if it's implicit. So in the case of the full model, we have this Rn xn equals 0, where the form of the O delta E residual is shown on the bottom there. And we get a similar O delta E for the Galerkin model. And the reason I've colored the bottom right square in red is that we showed in some of our work that it's impossible to generally demonstrate that the time discrete Galerkin solution associates with any notion of optimality with respect to the time discrete full order model solution. So even though our time continuous approximation in the top right corresponded to a residual minimizing approximation, which is some notion of optimality, that property of optimality is lost after we introduce time discretization. And it turns out for many problems, especially in turbulent flows, this can lead to very substantial problems. And it's well known that sort of POD Galerkin methods don't work well for compressible turbulent flows. And so
I have a question here. So what is the accuracy of the linear projection, and how do you make sense of that? Like under what condition is this linear, this phi is a reasonable projection?
Right, so I'm going to talk about this a bit later on in the talk. Basically, you can characterize like how good a phi can be from the Kolmogorov width of the problem, which is sort of a mathematical property of the underlying solution manifold, and how well it's representable by a linear subspace. So it depends a lot on the problem at hand. So for example, if you have a diffusion dominated problem, those are characterized by fast decaying Kolmogorov widths, which means that basically, if you think about it intuitively, a small number of fixed spatial modes can accurately represent diffusive phenomena. In contrast, if you have sort of a propagating shock, for example, that is not well characterized by any low dimensional subspace because you have like a discontinuity that's moving. So the amenability of your problem to a low dimensional subspace approximation is defined by this mathematical quantity known as the Kolmogorov width, which I'm actually going to talk about a little bit later on.
Okay, great, thanks.
Yeah. So our idea, this is now about 10 years old, is rather than optimizing and discretizing, if you flip the order and instead discretize then optimize, you can obtain a residual minimizing approximation at the time discrete level, which yields this so-called least squares Petrov-Galerkin or LSPG ROM. And we have a whole host of different papers that do various analyses on this method with respect to Galerkin. And it turns out that in many cases, this actually performs much better than traditional Galerkin methods for stiff problems. I also want to point out we have a recent paper that generalizes LSPG to just basically least squares projections over finite time windows that are larger than just the time step. So just to give you an idea of how well LSPG works, here is this captive carry problem I showed a few slides ago. The high fidelity model is characterized by about 1,000,000 degrees of freedom and 10,000 time steps. So let's see how well LSPG works on this problem. So here is, I've written on the top of the slide here, the least squares formulation that arises at each time instance. Just solving this least squares problem by itself is actually quite costly because we're minimizing the sum of squares of 1,000,000 elements of this residual. So what we do is introduce a sparse semi-norm, which is known as hyperreduction in our field. And what this allows us to do is effectively only evaluate the residual on a subset of the mesh, which is here shown in red. So it's about 1% of the original mesh. And this is nice because it allows us to basically achieve n-independence operation counts, which allows us to do HPC caliber simulations on a laptop. And just to demonstrate the success of that, so here is this cavity flow problem. The top row is this LSPG ROM. The bottom is the high fidelity model. In this case, Galerkin was completely unstable. You see that the LSPG ROM ran in half an hour on 2 cores, whereas the high fidelity model ran in 5 hours on 48 cores. So we are hitting that articulated criteria that NASA laid out of 200x savings in core hours with sub 1% errors and drag. So if these results are so promising, hopefully they look reasonably exciting. Why doesn't LSPG ship with every computational physics code that you download from the internet? And that's something that we're actually trying to address in our work. And there's a whole host of things that need to be improved before this is like production capable and widely deployable. But I'm going to sort of go over three kind of concrete shortcomings of this methodology and like standard model reduction methods, and how we've sort of worked to overcome those using deep learning methods. So what are outstanding challenges in model reduction? So number one, this relates to Professor Darv's question, which is basically the assumption that there exists any linear subspace that can represent your solution is actually an incredibly strong assumption. So you can envision very simple academic problems like one-dimensional Burger's equation, where you have a shock moving left to right, which I'll actually show later on. And there you can convince yourself that if you use an Eulerian description of the problem, there exists no low-dimensional linear subspace that can accurately represent that solution. And so to get around that, we've developed a method that leverages deep convolutional autoencoders and projection onto continuously differentiable nonlinear manifolds to overcome this sort of fundamental limitation of linear subspaces. Number two is that in general, important physical properties are not enforced by model reduction, right? I presented here a few slides ago, both Galerkin and LSPG, which each are characterized by residual minimizing approximations. But as you'll see here, I did this in sort of a physics agnostic way, right? I didn't know sort of how this residual was derived. Was it derived from a finite element formulation where there's some kind of underlying variational property I would want to satisfy? Does it come from a sort of a finite volume model that is a discretization of the integral form of conservation laws? I didn't really think much about that. I just introduced these residual minimizing approximations. And so we've done some work to actually modify these approximations to guarantee and enforce physical properties are satisfied in the resulting reduced order model. And number three is that error analysis has been traditionally very difficult. So if you follow the reduced basis literature or the model reduction literature in general, you'll know that the error analysis in our field is dominated by deriving a posteriori, rigorous a posteriori and a priori error bounds that are often extremely pessimistic in nature. And so what we've done is basically formulate that problem as a regression problem and sort of tackled it with LSTM networks and basically shown that you can get near perfect predictions of errors using some machine learning ideas. So I'm going to go through these sort of as an outline of the rest of the talk. So let's first talk about the linear subspace approximation assumption and how we're going to overcome that. So as I alluded to in my response to Professor Darv, there is a rigorous mathematical way of reasoning about the amenability of a problem to an approximation with a low-dimensional linear subspace, and that is the Carlberg width of the problem. So to introduce this notion, I'm going to first introduce sort of two mathematical entities. The first is calligraphic M, which is nothing more than the solution manifold, right? So it's the set of all solutions over all time and all parameters. And the second is the Grassmann manifold, which is just the set of all p-dimensional linear subspaces of Rn, right? So this is just the set of all subspaces that we could use for approximation. So what is the Kolmogorov width? The Kolmogorov width is the infimizer over all p-dimensional linear subspaces of p infinity m and s, where p infinity m and s is just the L infinity projection error of the solution manifold onto that particular subspace. So that's a bit of a mouthful, but the way that I would interpret this is basically if the Kolmogorov width for a problem is small for a given value of p, we know that there exists some p-dimensional linear subspace that can accurately represent every element of the solution manifold. Right, that's sort of the intuition for this. And the decay of the Kolmogorov width basically is how does dp of m change as you increase p, right? We'll know it monotonically decrease, but how quickly does it decrease? So to make this actually computable on a problem, so I can show you some plots, I'm going to replace this p infinity with p2, which is just the relative L2 projection error. So given this modified notion of the Kolmogorov width, I'm going to show you how this decays for a canonical problem in fluid dynamics, which I'll explain what this problem is a bit later on. But this is a pretty typical curve that we get in our field, where this Kolmogorov width decays exponentially as p increases. So given that, we can actually compute the relative L2 projection error of the solution manifold onto my POD basis, which is coming from data. And if we do that, we obtain this blue curve. And so the gap between the blue curve and the black curve is really the training deficiency, right? So with infinite training data, this blue curve would collapse onto the black curve. But in this case, we did a relatively good job with training. If I then solve an LSPG reduced order model with that basis, then I obtain a sequence of green points as shown here. And the gap between the blue curve and the green curve is really the closure error. It's basically the failure of the reduced order model to recover the optimal approximation in that subspace. So these two errors are often discussed in our field, and there's a lot of intuition and work that's gone into that. But but very rarely does anyone really talk about how good is this Kolmogorov width decay. So we see here it's exponential, but is that really a good result? Like, what's a good sort of intuition for whether or not that is a good result for this problem? And so it turns out in this case, for this particular example, we have two parameters, so mu1 and mu2. And what that implies is that the underlying solution manifold has a dimension of at most 3, because we know that there's a unique mapping between 3 numbers, time, mu1 and mu2, to the solution vector. So that provides a parameterization for a 3-dimensional manifold. And so this gives us a way to reason about the Kolmogorov width limitation of this problem, which is that when even the optimal linear subspace is of the same dimension as the true underlying solution manifold, we have a substantial error in our approximation, right? So in this case, we have a roughly 5% approximation error, even if we use the theoretically optimal subspace where P is equal to the dimension of the manifold. And so this is a limitation you cannot overcome with even infinite training data. And it's incurred by the fact that you're using a low dimensional subspace to approximate the solution. So the goal of this work is really to overcome this fundamental limitation by introducing a nonlinear trial manifold for the kinematics. And so we are not the first people to observe that this is an issue in model reduction, but I would argue that there's a lot of room for improvement over what's been done up to this point. So the dominant category of approaches to tackle this problem basically try to either transform or update the linear subspace so that it can represent things like moving discontinuities. And while these approaches often work much better than just a fixed global POD basis, they often require very specialized problem knowledge. So some of these methods even require knowing exactly how a discontinuity is advecting, and then they advect the modes along with that discontinuity. And so that is almost sort of like a chicken and egg problem, where if we knew how the shock was advecting, then we've already kind of solved the problem. So the practical utility of some of these methods is a bit questionable. And these also don't consider manifolds of general nonlinear structure. They're always going to be local linear manifolds. The second approach basically does an a priori construction of local linear subspaces for different regions of the space or time domain and state space. And again, these are sort of local linear manifolds that aren't general in their structure. And the final category is closer to what we want to achieve. We basically, at the time that this was written, could find basically 3 papers in the literature that tried to do model reduction on nonlinear manifolds. Unfortunately, 2 of them were kinematically inconsistent, meaning that the velocity was not enforced to live in the tangent space of the manifold, which is sort of wrong out of the gate. And the other one was sort of limited to piecewise linear manifolds. And the solutions also lacked optimality. So what we tried to build here in this approach is a methodology that both overcomes the shortcomings of existing methods. So we want to consider general structured manifolds. We want to, of course, enforce kinematic consistency, and our approximations should be optimal in some sense. And we also want practical manifold construction, right? We don't want to need to require knowledge of how different discontinuities are moving or advection speeds to make this practical. And in particular, we want the same kind of turn the crank methodology as POD, where I'm given snapshots and I produce a nonlinear manifold. So to do this, we first develop a new projection framework that we're calling Manifold, Galerkin, and LSPG, which requires no deep learning or anything. It's just differential geometry and dynamical systems. And for the second part, we're using deep convolutional autoencoders to compute this, to compute the manifold. So I'll first talk about sort of the new projection scheme. And I'll do this in sort of an intuitive sort of high level manner. If you want details, you can look at our JCP paper. So first I'm going to go through what I already presented to you, but in a more graphical way. So previously we talked about POD basis as providing a linear trial subspace, which can be defined in this way. So the range of phi is a set of all solutions phi x hat with x hat and rp. And so if n equals 3 and p equals 2, POD basically is saying that the solution must exist in some hyperplane. By saying the solution exists in that hyperplane, we have this algebraic statement. If we apply the chain rule, we see that the velocity must also live in that very same hyperplane. So how do we extend the same kind of setup to nonlinear manifolds? We're going to do that through the introduction of a parameterization. So we're going to actually view the manifold from the extrinsic view, and it's going to be defined through this parameterization function g, which is a continuously differentiable mapping from Rp to Rn. So if we do that, then we can imagine that now instead of a hyperplane, we're learning some kind of curved manifold, in this case in 3 dimensions. So if we enforce our solution to live in that manifold, we basically say it can be expressed as gx hat algebraically, which clearly enables general structure. And number two, if we apply the chain rule, we see that the velocity must live in the tangent space of the manifold at a given point, in state space. So the velocity is always expressible as a linear combination of the columns of the Jacobian of this parameterization function G. So these are the kinematics. This describes how we're going to allow our solution to evolve. What are the dynamics? So in the Galerkin case, if you recall, we were in the linear subspace case, we were given phi. And we derived the Galerkin model by introducing a residual minimizing approximation, right? So we stated this, and then we showed that this is actually equivalent to this low-dimensional ODE system. In an LSPG, we directly minimize the time-discrete O delta E residual, right, which is shown here. So now if we make the same kinematic, if we make the same sort of, if we can pose the same optimization problems, but over the new kinematic restrictions and yield Galerkin and LSPG counterparts that are applicable to nonlinear manifolds. So if we do that, we imagine we're given G, then our velocity is going to be the element of the tangent space at our current point on the trajectory that minimizes this L2 norm of the time continuous residual. And you can show actually that that is mathematically equivalent to this low dimensional ODE system. And so the nice thing about this ODE system is that because it evolves in a low dimensional Euclidean space, you can employ any time integrator you want and you're guaranteed to live on the manifold. You can never get off the manifold because we're dealing with sort of the latent variables from which we can recover an element of the manifold through this parameterization function G. So that's sort of a nice attribute. We can use any Runge-Kutta scheme or linear multi-step scheme or whatever your favorite integrator is for that system. Analogously, for LSPG, we can introduce a time-discrete residual minimizing formulation that now operates on G of V hat. And so in both of these cases, we have residual minimizing properties. And we show in our paper that there's a nice relationship between manifold Galerkin and manifold LSPG in the following sense. So if we have a twice continuously differentiable manifold, the differences in the solution increments can be bounded by the time step over which that increment is taken. And we take the limit of the time step going to 0. These are actually equivalent models, which is sort of intuitive because what this is effectively saying is that under smoothness assumptions, time discrete residual minimization becomes equivalent to time continuous residual minimization in this limit. So that's a nice sort of theoretical connection there. The other thing that's nice is that we can derive rigorous a posteriori error bounds. And thinking forward to the fact that we're going to construct this G from deep learning, we are able to basically, what this means is we're able to rigorously certify the predictions we're getting from our deep learning model in sort of a rigorous mathematical way, which is somewhat uncommon when you're talking about sort of generalization properties of deep learning models. So under assumptions of Lipschitz continuity and a sufficiently small time step, you can derive similar error bounds that are time local a posteriori bounds for both the Galerkin and the LSPG models as shown here. In particular, the term on the right is the recursive term in the bound, which is identical in both cases. What's different is the colored term. And what we see here is that this is just the L2 norm of the residual, which is in fact what is minimized sequentially by this LSPG model. So there's some intuitive reasoning as to why the manifold LSPG model might be superior to the Galerkin, because we're basically minimizing the error bound sequentially in time. So that's nice theoretical justification for that model. So this is the setup. I assumed this entire time that we had this parameterization function G at our disposal. How do we construct that from training data? And so what we're going to do is, as I alluded to earlier.
Evan, can I ask a quick question? So you're always evolving on the tangent space if you do it this way? Is that what you're saying? Or?
So yeah, you're basically always evolving on the manifold itself.
On the so you're not okay. So you're not even on the thing. Okay.
So you're always staying on the manifold because if you think about what we're computing, we're always computing these latent variables that the decoder that the parameterization function G is applied to, which is by definition restricting the results to live on the manifold.
Okay.
And the key here is that we're basically using this extrinsic view of the manifold to guarantee these properties.
Okay.
Okay, so how do we apply deep convolutional autoencoders to do this sort of thing? So I'm going to assume no one has heard of an autoencoder and just briefly go over why we're using it and how it relates to this parameterization function. So an autoencoder essentially tries to copy inputs to outputs through this particular kind of architecture that narrows to a small set of numbers at the center of the architecture. The first part is known as the encoder, the latter part is known as the decoder. And what we're going to do is basically use this autoencoder as a mechanism to try to represent all of our state snapshots that we see. And so you can imagine that if I'm able to successfully copy every snapshot of the state that I've seen to its output, then the latter half, or the decoder of this autoencoder architecture, provides the exact thing that we want from our parameterization function of the manifold. Namely, it provides a mapping from a low-dimensional space to the high-dimensional space, and we know that the codomain of this function is very capable of representing all the solutions that we've seen over our training. So the idea is we're going to use an autoencoder deployed on our training data to build this parameterization function of the manifold. And the reason we're using convolutional architectures is essentially because we're leveraging the connection between image data and spatially distributed PDE data when you're using an Eulerian viewpoint. So we want to have a lot of the same sort of inductive biases that go into our model, like translational invariance, the preservation of sort of local features, and so on. So this is why we're using sort of a convolutional architecture. So how does this map to this training machine learning reduction workflow that I mentioned earlier? So training is identical to what we had before. Recall I formed this snapshot matrix X, and then rather than computing the singular value decomposition, what I'm going to do instead is introduce an autoencoder architecture, attempt to copy every column of X to a counterpart in X tilde, and I'm going to train the network to minimize the Frobenius loss of these two quantities.
So can I ask a question?
Yep.
Yeah. So can you comment a little bit on the following? I mean, like, it's more like the overall philosophy of what you're trying to do. So I understand you have this linear projection, and now you're looking at this nonlinear autoencoder kind of approach. But so you're assuming that you have this data X, which I guess comes from high fidelity simulations, and then you're trying to build this this reduced total model. But so in what sense is the model you're learning sort of transferable, or can be used in a more predictive, in a predictive manner, right? Because obviously, if you have generated the data that comes from a certain setup, simulations, boundary conditions, what have you, you build a reduced order model for that problem. Okay, but you already have the solution to that problem. So yeah, you want to use that in a different context, or in a more predictive manner. Yeah. So can you comment a little bit on that, or yeah?
Sure. Yeah. So basically, there's sort of two answers to that. Number one is we need to know if it's not working online, right? So we have to have some kind of error indicator that suggests the ROM is not working. And that's actually the third part of my talk. We have an error model that we're building to detect when it's not working. And then how do you somehow improve the prediction? And so we have a body of work, actually. We have a paper that was recently published with Philip Etter at Stanford, where we show how to refine a ROM a posteriori when we're using linear subspaces. And the idea there is it's sort of analogous to mesh adaptive H refinement, where for like a spectral basis, where you can basically split up a given basis vector into multiple vectors, that sort of together span that original vector. So you can basically add predictive fidelity to the model. In the nonlinear case, so we actually had some work going on before I left Sandia. We were exploring transfer learning. So if we detect that our model's not working well, you can imagine retraining part of the network online to minimize the residual of the true online problem, right?
No, but my question was more, well, I mean, perhaps this is a partial answer, but the question was more trying to understand, this reduced order model, it's built for, let's say, for given boundary conditions, for given geometry, or what, sort of what can you vary? What parts of the problem can you vary while maintaining the validity of the reduced order model? If you understand my question.
Yeah. So basically, I mean, the way that we're mathematically encoding all those dependencies is through that parameter vector mu, right? So the parameter vector mu basically encodes all the different parameters that could vary in the simulation, whether it's boundary conditions, geometric parameters, design variables, and so on. So that's all captured in that mu vector. And so when we train our model, what we should be doing is sort of spanning the space of the parameter domain that we're allowing those parameters to live in. So yeah, so that's sort of like how we're dealing with all those parameters entering the picture. The question of is it guaranteed to generalize? The answer is definitely no, because you're only as good as what your training data are telling you. So that's sort of why we have this sort of two-part solution to that, which is one, detect if the model's not working well, and number two, somehow refine the model online to improve the predictive fidelity of the model by essentially adding the ROM.
Okay, but the idea then is okay. So the idea, if I understand it, then is you have maybe some design parameters that you're interested in varying for control, optimization, design, what have you. So the idea is you may, for example, just to give a number, sample 1,000 of these new values in the training set, build your ROM, but let's say later on in your design phase, maybe you need to evaluate at 100,000 views. And you assume that the training set was sufficient to establish the validity of ROM for a larger set of new values.
Yeah, so we hope that that's the case. And if that's not the case, we need to basically be able to detect that we're not accurate, which we have a model for.
Sure.
And then also refine the model so that you actually add degrees of freedom to the ROM so that it can actually like make predictions that were outside of what you saw during training. And so for that second step, that's this a posteriori refinement mechanism that we've already developed for linear subspaces. And for this nonlinear autoencoder, the idea that we are working on is effectively you free up some of the parameters in the neural net for retraining during the online prediction stage, because recall that we're always feeding these into this residual minimization of projection. So we're guaranteed that as we like add fidelity to the model, we'll monotonically reduce that online residual, because we're always like our prediction stage is always going through the physics model.
But you have an example where you vary. I haven't seen that. Do you have examples where you vary this mu or look at what's required? What mu's were used in the training versus what range of mu's might be accurate, or I don't know, applications where
so it's
going beyond the training data in some sense.
Yeah, so it's very problem dependent. And it's hard to know a priori like exactly what regions of the parameter space are going to be hard to predict given like the training data for generally like practical problems. So yeah, we have a lot of examples where you can train it in sort of using like Latin hypercube sampling of the parameter space. Then when you deploy it at some points in the prediction stage, it doesn't work well, which is when we then allow the ROM to be refined online through exposing additional degrees of freedom. And I can show you, I didn't have it in this talk prepared, but I can show you maybe at the end a few like little vignettes of how we've been able to do that in the linear subspace case.
Okay, thank you.
Yeah. Okay, so returning back to this picture. So once we train this autoencoder, we define our manifold by setting the parameterization function equal to this decoder. And I want to emphasize that this is kind of a big breakthrough in model reduction because it allows us to generate a general nonlinear manifold in a way that requires no specialized problem knowledge at all. It's a similar turn the crank methodology to POD, which is pretty nice. Okay, so I want to return very quickly to what I showed earlier in the reduction. So the reduction step, which is the projection, is effectively this manifold ROM approach with both Galerkin and LSPG models shown there. And I want to emphasize, this kind of gets at Eric's question a bit, which is that we actually are directly integrating deep learning models now with the residual that's coming from our physics model. So these G's here are coming from our autoencoder. The R is the actual physics derived residual that comes from our physics code. And so when we run our predictions online, we're actually pumping these deep learning models into the physics model and minimizing the associated residual. So this is our sort of our key into both parts of what Eric was getting at. Number one, it provides us a window into how accurate our model is. So intuitively, if the residual norm is large, then we know that our model is not able to generate accurate results. And number two, it provides us a mechanism to like actually refine the prediction in the sense that if we can basically add degrees of freedom to our latent space that G is acting on, we can improve the predictive fidelity of our model. So the second of those I'm not going to talk about, but I will talk about the first of those a bit later on. So let's see very quickly how this works on some academic problems. Right now, this is being implemented in the large scale code at Sandia. So we have one-dimensional Burger's equation, 2D reacting flow. Each of these is characterized by two parameters corresponding to like reaction terms or boundary condition terms. And we're going to use a deep convolutional autoencoder, 4 convolutional layers, 2 fully connected layers on either end. And again, this is the parameterization of the manifold. So just to give an idea of like how this works well. So in the Burger's example case, what I'm going to plot on the left here is the full order model solution. In the middle, I'll plot the projection and reconstruction with POD of dimension 3. And so on the top, this is just like basically tracing out something in R3. On the bottom, it's basically applying phi to the generalized coordinates x hat. And so what we see here is sort of what would be intuitive, which is that a POD basis of dimension 3 has no hope of capturing a moving discontinuity, right? Because it's basically prescribing 3 spatially fixed modes that you can take linear combinations of. So what I'll show now is the exact same plot, but with this autoencoder, but of the same exact dimension and the same exact training data. And what we see is effectively perfect reconstruction, right? So we see that it's tracing out some trajectory in latent space, but the reconstruction, because it's a nonlinear decoder, is almost able to perfectly reconstruct this moving discontinuity. So this is sort of getting right at the heart of what sort of why model reduction methods don't work well for advection dominated problems generally. And this provides you know, a real concrete mechanism to overcome that Kolmogorov width limitation of linear subspaces. So now let's introduce a reduced order model. So that was just the projection.
Kevin, can I ask a question?
Yep.
And feel free if it's better to discuss this at the end. But the can you comment on the actual architecture you're working with? Like, what are the inputs and the outputs and so on? Because we've been doing a lot of work looking into the approximation theory of deep neural networks and how nonlinear approximation works and so on. And so I'm actually pretty shocked at how good those results are. And I'm curious if you can give any more intuition, because we've actually been struggling quite a bit to understand a pretty similar problem.
Yeah, so all the details are like in extreme, you know, all the extreme details are given in the JCP paper, and Kuchin at Sandia could probably tell you, he'd even give you the code, I'm sure. But basically for the one-dimensional problem, we're using one-dimensional convolutions. And we're using, as I mentioned, sort of 4 convolutional layers. I don't remember all, we're using, so one critical thing is we're using exponential linear units because we require continuous differentiability. And we found if you use ReLU, then it doesn't work at all. So like the activation functions are really important, it turns out, for this application.
And it's just stacked LUs and convolutional layers. That's it. There's no other magic to it.
And then at the end, there's 1 or 2 fully connected layers that go down to the latent space.
And those are also ALU, is that right?
I believe so, yeah.
Yeah. Okay, interesting. Thank you.
Yeah, but the accuracy of the prediction will also depend on the training set and what you're training on. So I mean,
exactly. So there's that sort of 3 things. There's the representation power of the manifold. Then there's the closure error. The representation power of, like, if it's a linear or nonlinear manifold. Then there's how good your training data were, and then for the ROM, there's also the closure error. So those 3 errors are what we need to keep track of in model reduction.
Right. Thank you.
Yep. Okay, so here's how the actual ROMs work in the LSPG case. The second row here is the POD LSPG model of dimension 5. We see it works extremely poorly. If we keep the exact same residual minimizing projection, the same exact training data, the same exact latent space, but now use an autoencoder instead of this POD model, we get the bottom row, where it's nearly perfect recovery of the original model. So this is, again, pretty exciting in terms of how much better we do than the previous state of the art in model reduction. So I'm going to return now to these plots I showed, and then I'll now introduce sort of what happens when we introduce these autoencoders. So recall the plot I showed earlier was actually this rightmost plot. That was the reacting flow example. On the left, I've also shown Berger's equation. So recall in this problem that there exists some low-dimensional manifold. There exists a manifold of dimension 3 that can exactly represent all the solutions in our solution manifold because the underlying manifold dimension is 3. So let's see how well this autoencoder does as we increase the dimension of the latent space. And what we see is in both cases, there's a substantial drop-off as soon as we hit the underlying intrinsic manifold dimension of 3. And so that's really, really nice, because in this case, what this means is we've nearly recovered the intrinsic underlying manifold of the problem, right? Which is pretty remarkable. And we see that we actually saturated that point. So there's some finite capacity of our autoencoder architecture that is not able to do much better than what we achieved for p = 3. If I then use that manifold and solve, with LSPG, I should point out quickly that we are much, much better than even the theoretically optimal linear subspace. So we're effectively able to completely overcome this Kolmogorov width limitation faced by linear subspace ROMs. If I then solve an LSPG model with this manifold, I obtain these pink dots, and the gap there is, again, the closure error. But what we see is that with respect to the original POD LSPG model, we're still orders of magnitude better. And so we're breaking this Kolmogorov width barrier that's traditionally plagued our community. And if I then plot the Lurkin counterparts, what I see is that, at least on the left-hand side in the Berger's equation example, the LSPG model is substantially better, right? So this sequential minimization of the error bound is actually a nice property that yields better performance in practice.
A quick question. So is it also related to the precision of your deep learning
Sorry, say again?
platform? Yeah, is it the related to the precision of your deep learning platform, like double precision or?
No, I don't think so. We're still like quite far from numerical precision in those cases. We're like 0.1% errors, so we're still like not close to machine zero.
Thank you.
Yeah. Okay, so the second thing I want to mention is that I want to address is the physical property issue with model reduction. So let's dive into sort of a specific case of a class of physical problems, which are conservation laws. And so what does this ODE mean for conservation laws that have been discretized by a finite volume method? So I know many people are familiar with finite volume schemes, but for those of you who are not as familiar, basically a finite volume scheme decomposes the mesh, the physical domain, into a set of control volumes over which conservation laws are explicitly enforced. And so what does that mean for the terms in the ODE system? So each element of the state vector is the average value of one of these conserved variables UI, which could be mass, momentum, or energy, over a control volume. The velocity corresponds to the contribution of the flux and source of that conserved variable within a control volume, such that the ODE residual basically tells us how much, the rate at which we're violating conservation for each control variable, for each conserved variable in each control volume. So if we then introduce a time discretization method, the O delta E can be interpreted, this is for an atom scheme, can be interpreted as the amount we're violating conservation for each variable, each control volume over a given time window. And so because the full order model by definition is setting these residuals to zero, what this means is that the underlying intrinsic structure for finite volume methods is conservation. And so that's in principle what our reduced order model should be inheriting from the full order model. So is that happening? So here are the manifold, Galerkin, and LSPG models. They're residual minimizing. And so what that means in the context of finite volume schemes is that they're actually minimizing either the rate of conservation violation or the amount of conservation violation over a finite time step. And that seems like maybe an intuitively good thing, but because the objective functions could be non-zero, neither is actually enforcing conservation. And so that could lead to spurious generation or dissipation of quantities that could be conserved, which can be problematic for especially long time integration problems that we often encounter in turbulence. So how do we overcome this? So we've done this analogous work for Lagrangian dynamical systems, but for the case of finite volume schemes, what we can do is simply modify the objective, the optimization problem by adding these nonlinear equality constraints that explicitly enforce conservation over prescribed subdomains of the problem. So the C operator is effectively an agglomeration operator that combines contributions from neighboring cells into sort of a subdomain over which we're enforcing conservation. So in a sense, this is sort of a multi-level scheme where we're exactly enforcing conservation over subdomains, and we're minimizing the sum of squares of residuals at sort of the original mesh level. And so if there's a feasible solution, and we have a lot of theory been developed for feasibility of these problems, then we are guaranteeing that at least some subset of the problem is preserving conservation law properties. And so what we've seen is that when we enforce global conservation, which is basically saying that there's one subdomain corresponding to the full domain, we often observe much better performance. So we have an error bound that we've derived for this case. I won't go into too much detail here.
Sorry, can I ask? So what I thought I just heard you say was that you could apply conservation over the subdomains, but if you just do it over the whole domain, it works better. Why would you ever break it? There's something I don't understand.
Yeah, I mean, so basically we want to introduce a general formulation, and because we didn't know a priori, would it be better to enforce conservation over just one global domain or over several subdomains? And through experimentation, we discovered, at least for our problems, that global conservation was the best in the end.
Okay, thank you.
Yeah. So in the interest of time, I'm not going to go into this error bound, but the sort of the takeaway message of this error bound is that if we're using linear subspaces, then you can prove that the quantities you're supposed to be conserving over the subdomains, the error in those is only dictated by sort of the error in the flux along their boundary. So this implies that as long as we're getting the flux close to right, we're going to be doing a good job of tracking these globally conserved quantities. So we have, so I'll just show you a few quick illustrations of this. This is not our full set of experiments, but it kind of communicates the main idea. So here are the results I showed earlier where we have just the POD and autoencoder manifolds. The errors are quite different in terms of the solution error, but in both cases, they're actually violating global conservation by a non-trivial amount. So even on the right-hand side with the autoencoder, we get a 1% violation in global conservation. So if we equip both of these formulations with this constraint, we obtain at very, very little additional cost similar looking results, but in both cases, we're actually satisfying conservation to numerical precision. And so that's really exciting for like sort of, especially long-time integration problems. So to bring it back to some interpretation, here are the conservative manifold Galerkin and LSPG models. The way I'm interpreting this is that we're actually directly integrating computational physics with deep learning predictions. And I would interpret this also as sort of a latent dynamics model that exactly enforces conservation. So there's a whole field in the deep learning community of latent dynamics models, where for some dynamical system, it is attempted to learn sort of what is an embedding of those states, as well as what is the associated time evolution. And most of those are data-driven in nature. So these are not purely data-driven, what we're proposing, because we're feeding the predictions directly into our physics model to generate a projection type approach. Furthermore, no existing methods in the literature can exactly enforce properties like conservation in the same way that this approach can. Yeah, and our quasi-Newton solvers are directly calling TensorFlow, and we're working on implementations. So I think I have a few minutes to talk about, this last part of the talk. Is that okay? Do I have a few minutes? Because we started a bit late, or are we out of time? I can also drop this last part.
Yeah, we're kind of probably need to wrap up because we had a pretty long morning, but yeah, maybe a couple more minutes. I'm not sure how much.
Okay, yeah, I'll just very quickly, I'll just in 2 minutes wrap this up. So this is basically how we use deep learning to do error analysis. And so the main point of this, and I'll just kind of jump to, the main point of this is that error bounds that we derive are often very pessimistic because they grow exponentially in time. And it's not uncommon for these error bounds to overpredict the error by several orders of magnitude. So what we've done is basically generate a a sort of analysis rooted approach to predicting errors. So this is like an error bound that we've derived, and we see that the error bound depends on non-local quantities in time. It also depends on the residual. So we're going to view this problem as sort of a regression setting where we're going to build a regression model that can try to predict the error directly using an architecture that respects these qualitative properties of traditional error bounds, in the sense that we want basically to be able to capture non-local dependence of the error, as well as be residual based. And so, yeah, we have a whole framework for doing this that encompasses a wide range of different time series models. And I'll sort of cut to the numerical result here, which is right here. So on sort of a benchmark problem, we tested our methodology with sort of a large number of combinations of regression methods on the left, and then different features that are residual based on the right. And in the top left, we're plotting the traditional Kennedy-O'Hagan method of modeling errors, which uses Gaussian process regression. And I'm plotting here the fraction of variance unexplained for each feature regression method combination. And what we see is that in our case, RNNs and LSTMs do the best, even though, we didn't want to just go with LSTMs because they're popular. We want to put it in sort of a rigorous testing framework, and we saw that it did work quite well. And furthermore, we get extremely accurate error predictions. So the FVU here is less than 2. Less than 10 to the minus 2, which means that our R-squared values are like basically 0.999. So we are generating nearly perfect error predictions with this LSTM model, which gives us an extremely nice model of basic idea of how accurately the ROM is performing when we deploy it in a real-time setting. So yeah, if you're interested, we have a few papers on this type of approach. So with that, I don't know if I have time for questions, but I'd be happy to take them.
So just a quick question with FVU, what's that? I didn't catch that.
Oh, FVU is fraction of variance unexplained. So it's 1 minus R-squared.
Okay, all right.
Yeah, so it's basically the sum of squared prediction errors so it's weird because we're predicting the error, but it's the sum of squared prediction errors of that error divided by the sum of squares of like the variance in the data by itself. So an FVU of 0 means that your model is exactly correct, perfectly predictive. And so that's sort of what you want this value to be as close to 0 as possible.
And so on the bottom, these are different inputs to your regression model that you're using, and then
Exactly. So these are different features. So the mu is if we just try to do the prediction with the parameters alone, that does really, really badly. And then this r hat g. So let's see, r tilde corresponds to an approximation of the residual. R hat corresponds to just samples of the residual, and r hat g corresponds to sort of like the generalized coefficients and a gappy PUV approximation. So these are just different features that require a small number of residual samples given by NS. So given by NR and NS. So in this case, we need on the order of like 7 to 10 residual samples to get extremely accurate error predictions.
Okay.
Ask another question. First, that was a really, really good talk. So if I understand it correctly, right, you're getting this nonlinear basis through the autoencoder. And then after the fact, in order to get conservation or whatever structure it is that you want, you're turning to equality constraint optimization in order to cook it back in and correct for it.
Yep.
And I guess I'm curious if you've looked into, it seems like it would be super straightforward to do something like pins in the autoencoder in order to try and cook, you know, some similar properties into the basis.
Yeah. So you're exactly right. We have some ideas along those lines in the works right now. I would say in terms of physical property preservation, I kind of view it from two viewpoints. There's like kinematic enforcement of those properties, which is sort of a property of the neural network itself, right? So if you make sure that your network is only generating conservative predictions, then you don't need to do anything on the dynamic side. So what we're doing is we're actually just saying, let's have like generic kinematics coming from an autoencoder. But then when I compute dynamics, I'm enforcing the dynamics to reside on like a manifold of conservative trajectories, basically. And so what you could do is bake in like some better knowledge of the manifold structure itself. So one thing we've thought of, it's not exactly pins, but it's related, is build a mapping explicitly from the parameters and time to the solution, right? So that would basically be like a kind of almost a supervised machine learning setup, not really an autoencoder. Then you could assign interpretations to each of those latent variables. But then you'd also have to like have like sort of a residual term that would like correct for any deficiency you have in that original sort of pin type network. Does that make sense?
Yeah, it does. I mean, I guess another question I had is if you've thought at all about, you know, so for, you know, conservation is one kind of physics structure, but there's other kinds like exact sequence structure and so on, where making the error small doesn't cut it for like Maxwell's equations and so on. Do you have any thoughts about how to get that kind of structure in there, right? Or have you looked at those kind of problems maybe?
So the only other class of problems we've looked at for this have been like Hamiltonian Lagrangian systems. And the approach is extremely different. Like you actually can't derive it in like a least squares way at all. The way that we get at that is sort of, if you look at how like Lagrangian dynamical systems are derived, you start with these like Lagrangian ingredients of like, you know, basically like the kinetic energy, the potential energy, the kinetic energy derives from this Riemannian metric and so on. And so what you have to do is make sure that you're preserving sort of all like the intrinsic structure of how those dynamics were derived. And so the way we go about that is we actually approximate those ingredients directly, then apply the Euler-Lagrange equations to those Lagrangian ingredients. So all the machine learning has to happen before you derive the equations of motion. So it really depends. It's hard for me to say like that there's like I don't think there's like one recipe for any set of physics you want to conserve. You have to really think about, you know, what physics are important for the problem that you're solving. How are they embedded in the high fidelity model? And then how can you like recover that sort of property through like a reduced, you know, through a model reduction lens? And it's not like the same crank that you would turn in every case.
Right. So the references that you presented, you feel like that gives the, you know, the best summary of your viewpoint on all this stuff so far?
It gives this, so those references are like, they summarize my viewpoint on conservation laws. We have another paper in CISC that is like Lagrangian dynamical systems, this is like, you know, like 8 years ago now. So that there was no nonlinear manifold stuff in there. That is like basically what we did for Lagrangian systems.
Okay, great. Thank you very much.
Yeah.
So one more question, Kevin, on the hyperreduction. Are you basically piggybacking off of the hyperreduction in your full order model? Is that what you're doing?
So the hyperreduction for this autoencoder stuff?
Yeah, for the autoencoder stuff.
Yeah, so that's actually an interesting point. We haven't done this yet. We're working on it right now. By we, I mean people at Sandia. But the idea there is actually like, because we're using convolutional architectures, you basically get a hyperreduction almost for free if you're a little bit clever with how you handle the fully connected layers. Because you can think of like what wouldn't work is if we have a sort of an MLP, like a fully connected multi-layer perceptron for the decoder. Because even if you inject sparsity at the output, you actually need dense layers upstream of that. But the nice thing about convolutional layers is they preserve sparsity. If they're acting on like a sparse like input, they're going to preserve that sparsity downstream. So effectively, the same workflow would, in principle, operate with hyperreduction as it relates to convolutional autoencoders.
Okay.
So
that's ongoing work.
Yeah, that's ongoing work, and you have to be like, it's a sort of a nuanced technical point to how you would preserve n independent operation counts with these decoders.
So I guess there are no other questions, or Eric?
Yeah, just a quick question on the software. So you mentioned TensorFlow, but how in practice, how do you couple your physics code, your PDE with the TensorFlow, or do you have something you can share there, or what's your?
So Sandia has been a bit hesitant to share any of the code that's been developed. My co-author Kuchin can probably talk more to that. But basically, I'm going to pull up the slide here.
But your approach is to use TensorFlow for the autoencoder aspects, and then somehow this gets connected into your physics code.
Yeah, exactly. So whatever you're, so it's analogous to POD. So the way that POD works is you put a POD basis in there that has the same number of degrees of freedom. It has the same number of rows as your original state vector, and so you can recover. Basically, there's like a chain of operations where you apply the POD basis to some low dimensional state that yields a high dimensional state that you can apply the residual to. So in the TensorFlow case, you basically like anything between the latent state and the output can be sort of non-interpretable to our physics code, except for the very final output, because that's viewed and interpreted as a state. So that's sort of like roughly how that workflow goes. You just have to make sure that the image of what's coming out of G is compatible with whatever your state is expecting. And also from a parallelization viewpoint, you can imagine like parallelizing G across like the network in a distributed memory setting, and only the part of the network that's going to project to those degrees of freedom needs to be available on that node. So it's sort of parallelizable in a somewhat easy way, I would say. And then when we call, so we solve all these models using quasi-Newton
model parallelism.
So yeah, I was going to say we solve all these with quasi-Newton methods, and the nice thing about that is that you can get this the requisite decoder Jacobian for free from backprop. So that comes built into all these codes. So that's nice. So we can use second order methods for resolving these optimization problems. So basically, it's like an SQP method that ends up calling backprop to compute gradients.
Nice. Okay.
Okay, I think, yeah, thanks again, Kevin, for a great talk.
Thanks.